So this one. What 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 you're trying to do here? Did someone send a message? Okay. What you're trying to do here is that you want to create a function. That like that's how machine works. Machine is more like a model. It just takes an input, process it here, just do an output. So your computer takes some input, does some calculation, and give an output. That's how a calculator used to work. An example is that if they give us 4 by 3, if you input 4 times 3 into a computer, perhaps what it does is I just convert it into an addition and just work with addition and just give an output for us. Because that's easier for you to work with this than just doing it 4 by 3. You see? And then we move on to what we just came here to say we want to take an example of what the computer does. We also want to do something similar. Just create a function that's similar to what the computer do. And we say we just want to convert our mouse. We just want to convert if they give us a value in kilometers, we want to convert it into what mouse. We want to convert it to mouse. And what we said is that we know the relation between them. The relation between them is just linear. The reason I'm saying it's linear because kilometers. That's mostly in Ghana here. That's where we use kilometers. But I think when you go to some other part of the water, they use the mouse. See, if like they say, let's assume that they say like 20 kilometers. If you drive 20 kilometers in Ghana here, it's going to take you 2 hours. And I'm sure if you also go to the different part of the water, use the mouse. The different parts of the water, use the mouse. Different parts of the water also use the mouse. And if you drive 2 hours in the same road on the same road, I think you're also going to cover the same distance. But just that now the distance rather in miles instead of it being kilometers. The distance rather in miles instead of it being kilometers. So what you're just trying to say is that since the distance that you cover, if you should cover if you are the same place, let's assume that I think we are all in Ghana here. All of us here in Ghana. And if we all know, let's say we all know that I don't know if you know the Independence Square. The Independence Square is having a field like a park, a small park there. If you stand at one end,
Please, please, I don't know there.
you don't know the Independence Square. All
Please,
right.
yes.
What I'm just trying to tell is that if you go here, let's say you're on a field, a park, and you stand at maybe one pole, you have 2 poles on a football field. You stand at one pole. Let's say Old Trafford is in Ghana here, and you have another Old Trafford also in let's say UK, and they're saying that UK they use this mouse to calculate distance. But in Ghana here, we use kilometers to calculate our distance. If I should stand at Old Trafford in Ghana here, and let's say I should just calculate the distance from one pole to other pole. If I have something like 20 kilometers, and I go to UK to then calculate the same thing from one pole to another pole. Even though they are not using kilometers, they are using miles. The distance they are going to get in miles, no, it's equivalent to the one we had in kilometers in Ghana here. It's equivalent, even though they're not. We are using a different unit, but the distance that they cover, maybe you should just convert one to the other one. It will be the same thing. It won't be different. That's why you're saying that I don't have laptop, so can I use my phone? Yeah, you can use your phone to join though. You can use your phone to join. Yeah, but yeah, you need to practice your laptop. Someone asked a question, that's what I'm answering to it. So since the distance that they covered, if you convert one to other one, it will be the same thing. But just like they're just using a different unit for it. That's why we are saying that the relation between miles and kilometers is linear. Meaning if you should be able to convert one to other one, the distance will be the same thing. Like the distance that you covered or anything that you covered will always be the same thing. So that's why we have written is like miles equals kilometers by c. And this expression here tells us that the relation between these two is just linear. The relation between these two is linear. All right. So now let's continue. So now let's see what you can do about it. So what you can do about it is this. Beautiful. What you can do about it is this. So for us to be able to convert this, let's see, they've given us, they've given us, they've given us this. They have given us this. And what they've given us is, we say we should just use the information they've given us here to be able to create a function. No, that's what we had. We had something like mass equals kilometers by c. That's the function we are having, because the relation between them is linear. So what we really want to do is to find the value for c, because if we should find a value for c here, and they give us a value in kilometers here, we'll be able to convert it into miles. You'll be able to convert it into miles. So the most important part here is what we want to find the value for c. No, mathematically, this is very easy for us to solve. See, but this I don't want to just do it in the mathematical way. We just want to do it like we don't know anything about maths. We just want to do it step by step. See. So now they've given us this data here. And this data they've given us here, I said this data is called our truth data. Our truth data, because that's this information what we are going to use to be able to get our value C. That means we are going to use to get our parameter. This C is called a parameter because we can take any value that will help to improve this function here. That will help to improve this function here. Even though we call this as a truth example, sometimes we also call this as our training example, our training data in the neural network or machine learning form. We also call it our training data. Now let's use this information here. Let's use the information here to be able to get the value for our C. First and foremost, you can see that when the value in kilometer is 0, the mass is 0. So we don't have to worry about even the first record. No, you see, we have 2 rows here. You can see this was 1. This is 1 record, and this is another one. And the other one's also 2. So I have 2 records here. Each row is just a record. Each row you see here is a record. Some can call it a record. Some can call it an observation. All of them is correct. I'm just trying to help you guys here, just to pick some things here. So let's see. So let's just assume that our C here is 0.5. If our C is 0.5, what can we do? You say if it's 0.5, and you plot it into a function that we're having. See, the function was this. 1 square kilometers by c. If you plot it here, you get an output of 50. Because 100 times 0.5 is going to give us 50. So then find our error. Our error is equal to our truth minus our calculated. So the truth value was what? The truth value we were expecting was 62.137. But this our model gave us what? 50. So the truth minus our 50 will give us 12.137. So that's the error we're having. And the error is very big or it's huge. And we can't deal with huge errors like this. See, because if you're having a very huge error here, meaning the other subsequent ones we're going to predict will also have some huge errors. And that won't be a very good model, because if someone should use this one to be able to drive, the person is going to make a lot of mistakes, or it can really lead the person to get an accident. So this error, we don't like it. We just want to improve this model or this function. And what we can do here is how to improve it. By you changing the value for C. You know, when it's 0.5, we are going to get it. Now let's try and increase it to 0.6 and see. So now we have increased it to 0.6. When it's 0.6, the value is 60 here. And when it's 60 here, the error that you're having is, the error is always the truth value minus the calculated value. The error you're having here is 2.137. 2.137 is what? It's less, like the magnitude is less as compared to this 12.137. So if we should choose between the two, we would prefer the second one. The second one is when our C is equal to 0.6. See? So this can be an error we might be happy to live with. But someone can say that 2.137 is still huge. So let's try and also improve it again. So let's see if we can improve it again now. Let's try and use 0.7. When you use 0.7, you're having what? 17. And when you use 70, so the truth minus our calculated, you can see the truth minus our calculated is rather giving us negative 7.8863. So the 0.7 was given us negative 7.863 as compared to when you use 0.6. 0.6 gives us 2.137. So between these two, which one do you prefer? Between these two, which one do you prefer? When C is equal to 0.7, when C is equal to 0.6, which one do you prefer? When you compare their errors. If it was C, which one will you go for? Zero point 0.6. Okay, someone says 0.6. Any other idea? Any other idea? Hey, Karim, Abdul Karim, are you there?
Yeah, hello, I'm here. Hello?
I think I met you. Yeah, Abdul, I met you like I think our last the second teacher, second edition of this one. I saw you there. Oh,
Yeah, I was there.
you also joined again. That's nice.
Yeah.
I think JT also said JT said he won 0.7. Okay, so who said 0.6? Okay, Fiawonu, why do you think 0.6 is better than 0.7?
Because you see, the 0.7 gives a negative number, and I don't know what it's. I think the 0.6 gives a positive number. That's why I chose the 0.6 instead of the 0.7.
Okay, JT, you said 0. You say you prefer 0.7. You prefer 0.7. So why do you prefer 0.7? So JT, why
I'm
do you
going for
prefer?
0.7 because I'm going for 0.7 because the error is a bit lower than when it's 0.6.
It's a bit lower. Okay, because
The
you
error,
know, okay, like when I check in, what you're saying is also true. Like we know positive numbers, they are greater than negative numbers. Okay, but one thing we need to know here is that anytime you're trying to predict something, it's better for us to undershoot than overshoot. What I'm just trying to say is that anytime you create a model and you want to predict something, it's a very important idea. I'm just trying to overlay for you guys. See, it's better for us to undershoot than overshoot. Undershoot meaning if you should calculate your error, it's better for error to be positive than for it to be negative. So we rather prefer what a positive error as compared to a negative error. And you can see that the 0.7 is not giving us what a negative error. And we don't like it. You see, I don't like it. So let's try and stick with the 0.6. Okay. So let's try and stick with the 0.6. So even though 0.7 give us a negative number, I think we can still improve it. How do you improve it? So instead of, you can see that we move from 0.5 to 0.6 to 0.7. And you realize that you had what? A value that was 70. We had a value that was 70. And since we don't want
So
something
can
that
we
is
use can we try 0 point maybe 6 something?
very good. That's a very good idea because if we should just increase it by zero, we're increasing it by 0.1. We're increasing by 0.1. So if you want to increase it by, let's try and increase it by 0. Let's try and increase it by 0.01 and see something. So let's try and use 0.61. So when you use 0.61, you can see that the error we had was what 1.137, and it was better than what we had for the other one when it was 0.6. See, someone can also go ahead and do 0.611, 0. Something like that, if we just to improve it. But I think 0.61 is good because it's giving us an error of almost 1.137, and that's preferable. Like very, we like it that way. You see. So one thing you should just notice is that we can see that the correction or how we nudge C. When you see how we nudge C, how we were able to like improve the value for C, it's a fraction of the error. Do you agree? When I say it's a fraction of the error, do you guys agree? Because one, we started with 0.5, then moved to 0.6, then went to 0.7. By the next one, we rather choose 0.61 because we realized that the error for the 0.7 was like negative or higher. But since we're rather getting close to the true value, we try to reduce how we improved. We try to reduce how we improved our value for C. So we can see that the error also helped us to try help us on how to nudge our C, like meaning how to improve the value for our C. So it's very important. So one thing I can say here is that the value for our C, if you are based on a modular, the value for C in a way depends on our error. The value for C depends on our error. So that's one important thing you should know here. One important thing you should know here. So let's move ahead. And you can see that what we have solved, we have not solved a problem exactly in one step, like we often do in math problems. Instead, we try solving it repeatedly. Some use the term iterative, and it means repeatedly improving an answer bit by bit. We call the above simple machine a predictor because it takes an input and makes a prediction of what the output should be. It takes an input and makes a prediction of what the output is supposed to be. So you might see this as a very simple math problem, but that's the basic of what neural networks are going to do. So if you don't understand it here now, when you move ahead, you can't understand it at all. So mostly those that have been able to finish this lecture or this course are those that really paid attention to the beginning. Because if you should join later, or you should miss the first two tutorials, I bet you can't continue following the tutorial again. All this is just step-by-step stuff. You can't jump one and just go to the next one. So if you really want to do it to completion, you just pay attention to even the small things we have been doing here. All right. So one thing you should know that they brought another term here, say iterative. The reason we are saying it's iterative because how we were able to improve our function. We didn't do it just once, like how we can just solve math problem like simultaneous equation or anything that we used to do. We can just solve it once, then we are gone. So I can see that this time we chose 0.5, 0.6, 0.7, and 0.61. We kept doing it one by one, so we were able to get a value that was close to the truth value looking, or a value that would give us a very small error. That's why we say what we solved the problem iteratively. We didn't do it just one, we just solved it iteratively. And the function that we had, the function that we used, we use that function to predict what? A number. We use that function to predict a number for the mouse. And that function that we used, we call it a predictor. A predictor. because you know that this function is just a simple machine that you see. We call it a predictor because you're using it to predict what a value or a number. You're expecting an output of it to be a number. So we call it a predictor. We do another one. We also do another one, but that one we are not going to predict a number, but we are going to predict a class. We are going to predict a label, a classification. And that one it won't be called a predictor, but rather it will be called a classifier. But this one you're calling it a predictor because you're using it to predict an output for a number. You know, number is an infinite number doesn't end, it goes on forever, it's infinite. So that makes it as a predictor. So you just take notes of these terms. You just take notes. I've talked about iteratively, predictor, model. Model is just like a function, you see, and like a function. And even predictor itself is also a function or a model. Predictor is also a model. So yeah, these are some terms that we just take notes of. So now let's go to classifying. Yeah, we are done with the predictor. Now let's go to classifying. So this is what we're going to do. We want to classify garden bugs. We want to classify garden bugs. And see the green ones are called ladybirds. And the orange ones are called caterpillars. And one thing you should just take note is that you can see that the ladybirds, the width, if you just check the width is very wide. Like the width really is really wide. Their value here, the value for the width is wide, but the value for the width for the caterpillar is very small. Okay, it's very small. And when you check the caterpillars, you can see that the length is long. The length here is long. But with the ladybirds, the length here is short. Okay. The length here is short. So that's something that we just take note here. It's something just take note. And we are still going to use our linear function or our model, like our y is equal to x. But you remember our kilometers problem, you have something like what? Mass is equal to kilometers by c. We are still going to use the same thing. Y is equal to what? Ax. Someone will ask that why we see this in y equal to x? Because he said he wants to classify something. Even though we are going to classify, but the main thing we want to do here is not just to classify like this one and this one. But rather we want to draw a line like this. This is our main thing we want to do. We want to draw a line like this. That will separate these two garden bags. I will separate these two garden bags. See, that's what we want to do. We want to draw a line like this. I will separate these two garden bags. So even though we are the main is to classify. The main idea behind just to get a line like that, I will separate the two garden bags. And so anything about line, you know, it's always in the form y is equal to x. Y is equal to x. And mathematically, any line that passes through this origin, meaning its intercept is 0. So when that's why you only see y equal to x here, you don't see anything like plus c or anything here. Because the origin is 0. So this is our truth example. With the other one, with the mouse, with the kilometers to mouse, they give us a truth example. We're training data. So we need a training data. Training data are examples of truth used to teach a predictor or a classifier. This time you're doing a classifier because you're not going to predict a number, but we just want to draw a line. I'll separate the two garden bags. So before you continue, I just want to have an idea for you guys. Like imagine give you something like this and you want to classify the two. What do you think you can do to be able to classify them? What do you think you can do so that you can classify this garden bags? Any idea? All right, so since we are trying to draw a line that will separate them, this is what we can do. Let's use our line. Now let's a equal to 0.25. If a is equal to 0.25, Then the line that we are going to draw is equal to y is equal to 0.25 x. And someone will say, well, why were you able to draw this line? How are you able to draw this line? Okay. This is how we're able to draw this line. We said the model you're going to use is equal to what? Y is equal to x. And I use y equal to x because just want a line that will separate them. That will separate those two. This is we don't want anything like a zigzag or a curve. Just want a straight line. That's why we are using y equal to x. And when we had a is equal to 0.25, we had a line like this. How do you draw this line? Okay, that's true. So to be able to draw this line, the only thing you can just do is you just have to take value from 1 to 10 or 1 to like 20, any number, anywhere you want to reach. So you just take value from 1 to 20. So when it gets 1, you just replace our x by 1. So 1 times 0.25, the value we get for y, then come and plot it like how we used to draw a graph. So width is 1, and this corresponding value in y, we just plot it here, we just draw. We also change x equal to 2. So 2 times 0.25, the value you're going to get, then come and plot here. The same thing, 3, you just do it here. What you get for y, you just plot it. 4, you just plot it. When you're done, you just draw a line. You just draw a line through all the points. And if you draw a line through all the points, you're going to get a line like this. You're going to get a line like this. But one thing you should know is that these lines we having, the line we're having here, it doesn't separate the two. It doesn't separate these caterpillars and ladybirds at all. It's below them. It doesn't separate them at all. You can see that is the value for A is not good at all. It's not good to separate these two caterpillars. But before that, let's take notes. How were we able to get these values? These caterpillars here. That's our truth example. We just plotted it on the graph. See, the weight is 3 and length is 1. So the weight of 3 is somewhere here and length of 1 is somewhere here. That's why we have this ladybird. And the other one is 1. The weight is 1 and the length is 3. So the weight is 1. 1 is somewhere here and our length is 1 here. So that's why we have this caterpillar here. So we plotted our truth data on the graph. See, that's why I'm seeing ladybirds and caterpillar here. And when it just equals 0.25, we had a line like this. We don't like it. So let's try and prove it again. Now, this is a bit different from what we did for the previous one. So you can see, let's see if we can find a repeatable recipe to do this. A series of computer instructions which computer scientists call an algorithm. Our desired output can't be 1. Let's try and pay attention to this side a lot. Let's try and pay attention to this side a lot. Say our desired output can be 1 if we are using the data point 3, 1. So we want to use our truth data here. We want to use our truth data here, 3 and 1. Now, when someone should put the value for 3, the output should predict is 1. But you should know that we don't want a line that will pass through this point here. That will pass through the point here, this ladybird caterpillar point. But rather, a line that will separate the two. So if we should use a data, if we should use this point 3 and 1, and we should replace this 3 into our function or our model, we don't want the model to predict 1. The reason we don't want this to predict 1, if it should predict 1, it means it's going to pass through the points 3 and 1. But rather, since we know that ladybirds, this one is ladybird, 3 and 1 is a ladybird. And from the guy, you can see the ladybird is what? It's around the side. So whether I want the line to be above the ladybirds, to be above the ladybird. So what you can do is we just have to replace the x here by 3. And we just multiply by something like a value for c here. And the value we get for y, that value shouldn't be 1. Because if it's 1, meaning the line is going to pass through this point here. But rather want a line that will be able to be above the lady beds and at the same time be below what the caterpillars. So this is what I'm just trying to explain here. So because we don't want the line to pass through the data point, it should be above the lady beds and below the caterpillar. So let's aim for 1.1. Why are we aiming for 1.1? Because we said what? We don't want the line to be able to pass through this one here. So we just added a small value to this 1.0 here. That's why you're having something like 1.1. You're having something like 1.1. Meaning now our new target data point is 3 and 1.1. Let's set A equals 0.25 million more, the Y is equal to AX. So this will give us Y is equal to 0.25x. Y equals 0.25x. And let's just try and replace the x value by 3. So let's replace x by 3. If we replace x by 3 in the model, we get y is equal to 0.25 by 3. We are going to get y is equal to 0.75. Is it confusing? What you're doing, is it confusing? Like, do you guys understand? Are you following?
Yes, I do understand.
You do understand? Okay, that's nice.
Sure, sure.
So if we should place this one, we have y is equal to 0.5. But when you check the true data here, the value for the length here is 1. But we said we want the value that's what's above the length 1. So we want something like 1.1. That's why when it comes, you can see 0.75 is too small because we were expecting to get a value of what 1.1. So here you can still find what an error here. So calculating our error from this new data point, we have error is equal to our desired value minus, because we know that error is equal to our truth value minus our actual output. So 1.1 minus 0.5 is going to give us what 0.35. 0.35. So this is our error. And when we're doing the predicting, if you can remember, when we do the predicting, we say that what our error, our parameter that we want to improve is in a way related to our error. Or that error help us to improve our parameter C. Now let's see the relationship between the error and our parameter C. Okay. Let's see the relationship between them. So there's a relationship between them. So we know that this is our error. To find for error, we know the error is our truth minus our y. Truth value minus our y is going to give us an error. That's why they say if desired minus actual output. And where from all these things we are seeing here? We are seeing all these things because of this. This y is what we had here. The y we had here is this. If you use 0.25, there is the line you're going to get. But we don't want this line. See, this line is y equal to ax. But we want a line like this. That will be able to separate the two garden bags. And you can see that if we're writing a plus change of a, meaning if you should get a value, you should add a value to a. You can add a value to a. That will help us to move this line from here to this place. And that value is what they are referring to. They are referring it here as change of what a. So this change of a can help us to improve the line from this side to this side. So this is our desired output that we want. This is our desired output. Our desired output. But this is what we had. The first one was what we had here. So we come here and say error is equal to our C minus Y, meaning truth minus our actual output. Or design minus our actual output. So you can see the desired here is A plus change of A times X. And our actual output that we had, the actual output is this one here. So minus our AX. The difference between them will give us our error. But if you check this one here, you can see that the difference between these two is our error. So the same thing I'm also doing here. So T minus Y is equal to this change we have seen here. So T minus Y is equal to this change here again. This one you're trying to factorize it. We open the brackets here. A times X come here. Change of A times X will come here. Minus our AX. Then we know T minus Y is the same thing as E. This T minus Y, the same thing as our error. That's why I just wrote E here. So it's equal to No, this ax and this ax is going to cancel. Mathematically going to cancel. Which is left with just our chain of a times x. Then we try and make our chain of a the subject. So if you make chain of a the subject, you're going to get e over x or e on x. So meaning for us to be able to get a value, that'll help you to improve our line. That helps to improve our line to this point here. The only thing we can do is just do this calculation. The change of a is equal to e over x. And see that when you add this change of a here to this our model we have in here, this one here, you can see when you add the two sides, it's going to give us a line that separates the two garden bags. So this is a very powerful formula you've gotten. It's a very, very powerful formula you've gotten. So let's try and see how we can implement this. So meaning so to adjust the parameter, that is to adjust a, we just need to divide the error by x. So like taking our point again, 3 and 1.1. We had an error of 0.35. So our change of a is just e over x. So e is our 0.35 divided by x. X was 3 here. So our change of a is equal to 0.1167. So if we should add this change of a to our original a, add it to our original a, that's what you're doing here. 0.5 times 0.1167 equal to this value here. So that's our a. So new model or new function is now rather instead of it being this one, instead of it being the first time it was 0. Plus y is equal to 0.25x. By this time we have improved it. So we are no longer going to use our 0.2 now. We are not going to use 0.25, but rather going to use 0.367. Because from all the calculations we did, we just wanted a value that will help us to separate these two garden bags. If we should use y equals 0.367x, and we should plot this on our graph, we're going to get this line. This is the line we're going to get. You can see this is the line you're going to get. And this line separates these two garden bags. These two garden bags. But one thing you should know that you can see that this is 0.366. It's a bit close to this value here, close to the green here, even though it's separated 2 here, but it's a bit close to it here. But let's leave that for now and let's try and still go improve it again, because the truth data they gave us, it wasn't only one value that they gave us 2 values. And we have used the first value here to improve our line. Now let's go and use the second value here. Let's go and use the second value here also to improve the line again. And in the second value, you can see it's about caterpillar. And when you watch the graph, caterpillar is around the side. So the line we are going to get, it shouldn't be above caterpillar, but rather should be below caterpillar. So the length here, that was 3.0. We are not going to put it to 3.0, but rather we are going to put it something like 2.9, 2.8, or 2.7. But all those values are below the length right here. But for us, we are going to use 2.9 to put it. So that's what you're doing here. So we come here. We just come here, just find our error. Replace 3. We have to replace 3 into this equation. So from the previous example, we know our target won't be 3.0, but rather 2.9, as I said, because we want the caterpillar to be below the line. So putting 1, why are you putting 1 into this one? Because our x is referencing our weight. Because the weight here is just 1. Okay, that's why I'm putting 1 into that equation. So putting 1.0 into our model, y is equal to 0.367 times 1. We get 0.367. And from what we did previously, we know we have to find an error. The error is 2.9 minus this one. Why is it 2.9? It's 2.9 because they wanted a value that is below this 3. That is below this, but not equals to the 3. So we find the error, and we find our change of a. Change of a is the value of a that when we add it to the original a, it's going to improve our line for us. We just find our change of a, just our error divided by our x. We get this value. So our a is equal to our original plus this, what we had here. So our a is equal to 0.9. So now new model now becomes y is equal to 2.9x. Y is equal to 2.9x. So if you should place this, the model here, if you replace x by 1 here, and see that line you are going to get will be somewhere here. You can see this is the line. So this is the line we had. Y is equal to 2.9x. So there's the line for y is equal to 2.9x. The previous one was 0.36x. But what have you noticed about these two lines that we had? You can see the first line when you use our green as our truth or our record to include the line. And the line was very close to our green here. The second one, when you use the caterpillar value to also include the line, see the line was also it's not close to the caterpillar line here. So now any value that we use to include the line, see the line will get close to that value. Will get close to that value. So how do we improve the line? So it won't always be close to the record that we use to improve our line or to write our line. So what you can do so that you help us to prevent this kind of situation is that we call something like a learning rate. We call something a learning rate. So that learning rate is just going to moderate how we improve our parameter or how we write our line. And with this thing, you can see that our learning rates here. A learning rate here, say what? This is our learning rate, what's L. So for us to be able to get our learning rate, we use something like a learning rate of 0.3. I'm saying the learning rate is just going to help us to moderate how we improve our error. Because when you check this formula here, to improve our A, to get our A, you just have to divide the whole error by the X and just take the whole value here. But instead of just taking the whole value for this A here, the chain of A, instead of taking the whole value here, we just want to take some of this value here. Some of the value here. So for us to take some of the value here, meaning we need to multiply this value here by a number which is less than 1. Because any number greater than 1 or equal to 1 will just give us the whole value of error here. But number which is less than 1, that is between 0 and 1. Between 0 and 1 will give us value that is less than this whole error here. So that's why you're using a learning rate here. This L here is called learning rate. It's a learning rate of 0.3. You can decide to use a learning rate of 0.4, 0.5 because they are all below 1. So learning rates. So when you take our first example, like what we did previously, initially the value was 0.25. We just do it, we get an error. And what's here? Instead of just doing our error divided by x, we've added an L to it. But the L help us not to take the whole of this like E over x, but I just take some of it. So we just multiply by 0.5, and this 0.5 is our learning rate. And if you should do this calculation and see our A here is 0.0583. And we add this value we had here to our old A. So our old A was 0.5. Why are we still using 0.5? I using 0.5 because that was what we are starting with. That was the initial value for our A. So don't think twice that previously we had a different number. No. We are still starting a new one here. And our initial guess for A is 0.25. So that's it. Okay. I think one of them.
Sorry, the 1.1. How did you get that?
All right. How did I get a 1.1?
Yeah, the 1.1 that you use for the error.
That's what our true example.
Okay, we're using the one from the previous example. Is it new?
When you watch this diagram, well, this is what I'm using our truth data.
Yes.
And the weight is 3 and the length is 1. you want to draw a line that is above this length. That's why you are using 1.1. I don't know if you get it.
No, I don't understand. You want to draw a line, but are we going to be told what the points, or we just have to know that it has to be above 1.1, 1 point.
This if you should draw the three, if you should draw this data point, this data, if you should draw this point here,
Yes.
one, the 3 and 1, if you should draw it, this so it will be somewhere here.
Yes.
And if you should replace this 3, if you place 3 into this function, you should replace 3 and 1 into this function. Even if you should just plot like 3 and 1 here, that 3 line will just be here. And when you should draw a line through this 3.1, it's going to pass through the point here. It's going to pass through this point here. But you don't want the line to pass through the point exactly. You just want it to be above the point. You want it to be above the point. That's why we use, instead of using 1 here, we're just using 1.1. You can decide to use 1.2 or 1.3. Because anything above the length, anything above this value 1 here will help to draw a line that will be above our point.
Okay, I understand.
Like, do you understand?
Yes, I do.
That's what we are doing. That's what we just did here. So we use 1.1. You had the error here. Then multiply it by our learning rate. You see the learning rate help us just to take a part of the error that we had or the adjustments we are doing. Then add it to our old value for A. So our new A is now equal to this one. And if you should just replace it, you should replace it into a model. Y equals 0.35 from the second. This one, they are also using the second data point here. The second data point they are using here. And you do something similar for it. They're going to get 1.2958. Add it to
But you had the added length to it.
they added what?
Length. I can see length brackets. Arrow divided by x. That's the formula for changing A.
No, all you're seeing here, I said it's a learning rate.
Okay.
Yeah. I said that the previous one when we were doing it. The previous one when we were doing it, you can see that like the line that we draw, it was always close to the data point we used. It was close to the data
Yes.
point we used. So that's why we are bringing this learning rate. We don't want just when you're doing the adjustment, we don't want to take all the adjustments. We just want to just take some part of the adjustment.
Okay, so is the learning rate constant? Because I've seen 0.5.
Yeah. For now, for this example, we're using 0.5.
Okay.
The most important is that the learning rate should be less than 1. It should be between 0 and 1. You see? Because anything above 1 is going to rather like improve or you're going to take the whole value for adjustment. But I don't want to take the whole value, but I just want to take just some parts of the value. So that's the reason why I'm bringing our learning rate. The learning rate, that's the way we're bringing the learning rate. So we can, when you do that again, you can see our A is equal to 1.6042. And our final model will be y equal to 1.6042x. And if we should draw this, on the graph, you can see that this is 1.6042. And this line perfectly divides the two data points. This 0.5, this 0.5 line was our initial line we were using. Then when you improve it to this part. Then we improve it to this final part here. And the final part perfectly separate these two gather as compared to the previous one. I see the previous one, the line we had was just close to the data point. The final line was just close to this one. You see. I just wanted the line just to be like between them, not separate them equally or perfectly. That's why this line help us to do. So we're able to do that using our learning rate. The learning rate adjustment we have for our change of A. We didn't take the full value, but rather we took just some part of it. That help us to improve our model. So the main idea of this tutorial today, like this session today, was for you guys to understand the power, the meaning, or the reason why we bring learning rate into our models. To bring learning rate into our models. So that was the main idea we did this classification. The other classification that we did was just to prove that the predictor was just to help us to understand that to be able to improve our error or to be able to improve our parameter in a way it's a bit related to our error. So meaning you can use our error to help to improve our parameter. But the second one we did about classification was just to help us to understand the reason why we add a learning rate into our model. So everything that we've done here, if you want to use the Python to just do it, Jupyter Notebook chairs, you can just do the same thing here. If you want to plot the graph and see that, oh yeah, this line really separates them equally, you can just do something like this, and it's going to work for you. It's going to work for you perfectly. Let me just try open my Jupyter Notebook and just plot this for you guys to see. Yeah, I'm coming. I'm trying to display it for you guys. Oh, right. I believe you can see it. You can see it now. Oh, this can you guys see it?
So should we open Jupyter Notebook?
Yeah, you can open
Should we
Jupyter
open?
Notebook.
Okay.
But if you don't have it, you can just watch it. You just want to draw the line so that you can see that it has separated it well.
Oh, I would actually love to follow your process also because I had issues with Jupyter Notebook earlier on.
Is it?
So I would have actually liked to follow your process because I had issues with Jupyter Notebook earlier on.
Oh, okay, okay.
This is the first time we're using it, right?
Today is the first time.
Yes, because I've not been in the previous class.
They, have you used Jupyter Notebook before?
Yes, but last time I had issues, so I just decided I should wait to use it.
Oh, but have you installed it? Do you have it on a machine
Yeah, I have it on my machine.
and it's working fine?
Yeah, it's working fine.
So you can just it's a very simple code. We just want to the what we have, the data point we have, we just want to plot it here and see if it can also produce it for us.
Okay. Uh, so can I screenshot what I have and put it on the WhatsApp?
What you having?
Okay, I'm having files running a cluster. So I should go to new file, right?
Yeah, is that you having a file running or what?
I'm having file running a cluster. I'm having localhost 889/3.
Okay, okay, 888. Okay,
Yes,
slash.
888/3. Yeah. So should I
So if I
open new
yeah
and Python 3?
yeah
Okay.
new, just open a new.
Okay, okay, I've done that.
Right.
Hmm.
Can you see the plot?
Yeah, I've seen the flow.
Can you see that when it was 0.25, when it was 0.25, the line you can see the line was not able to separate the 2 points well. Was not able to separate the two garden points well. But when you use the original one, like the one we had through the value we had through the when we added the learning rate to it, you can see the learning rate was
So if I input everything you inputted there, it's gonna then I run it, it's gonna bring up the chart, right?
pretty. Yeah, if you write everything there, it's going to bring a chart like this.
Okay, let me just do that.
Yeah, Fiona is still there. Eto, Fiona. Ikechukwu, have you been able to do it?
I'm currently still inputting it
Oh,
because I'm using my phone to view the videos and using my laptop
to type it. Oh,
yes, type it.
Let me each of right like him. Please let me know when you're done. Hello.
All right, no problem.
So if he's able to type it correctly, you can see that the line will be able to separate the two data points.
So should I use the 1.060?
Yeah, use that one.
As in the one you just changed right now.
Yeah, use that value. That's the value you had from when we were using when you're calculating. That's the value you had.
I'm just basically copying what you're doing. I just want to see how it presents itself on my screen.
Yeah,
Just
yeah.
want to see
So
the plotting.
yeah, you can run it. Do you know how to run it?
No, I don't. I don't.
When I'm
So I'm
done,
done
just
inputting everything.
yeah. So just you can just click on this place, run. It will run for you. Like, have you seen it?
It's bringing up a new IN this thing.
No, go to, like just
It's not
let
running.
let the cursor be in the cell, like in this cell. You see, let the cursor be in this cell,
Okay.
and then you run it.
Okay, see attribute error. Trace back most recent call last.
Can you share your screen? Can you share your screen? Let me see something.
Okay, because I'm using my phone. Let me
Oh,
come in through my laptop and see. Let me come in again through my laptop.
okay.
Should I share my screen?
Yeah, you can share your screen. You can see the error you're getting.
So how do I share my screen? Because you can't find the.
You see the icons below.
Yes, I'm seeing mute video CC the hand.
See you see the last bar two icon.
Okay, the one that has the three this thing dots.
Which one? No, like the one close. No, the on the left side. That dot, the three dots, the one on the left side.
Okay, present your entire screen. Okay, no problem. Do you see my screen?
It's not loading. Okay, I've seen it now.
With the attribute error.
All right. It's a matplotlib don't have attributes plt. Matplotlib.py plot. But have you installed it? Did you use Anaconda to install it?
Yes, I did. But I just opened it by searching and clicking on Anaconda Jupyter. I didn't open Anaconda to do it.
Okay. Well, let me check. Let me check it again. Okay, don't use see the third line.
The one that has PLT.
Yeah, I think you should do it plot. PLT plot. PLT dot plot.
PLOT, right?
Yeah, PLT. Then count it down one to him. Do it the down. Do it PLT and plot.
Okay.
Then run it to you see.
Okay. I think that was the issue.
Yeah.
You can see what's going on, right?
You've made it red. You can just change one to green. The one with one thread, you can do it green.
Okay, so instead of RO, I should use GN.
GO, yeah, GO.
Oh, okay. Okay.
Yeah. So that's how you can separate it. It means like what we're doing. So it's working now.
Okay.
Yeah. So, but the most important thing is for you to understand what the learning rate is. We'll use that one in our next tutorial.
So, but okay, you did basically the same. Why did you do plot PLT.PLOT XY then negative R? What does negative R stand for?
Okay.
You had a negative R there.
The
That's the last line.
If you want to draw a line, if you want to draw any line, mostly like normally you just do x equal to 1, x equal to 2, x equal to 3, just to place it into our equation.
Yes.
So this thing you're seeing here is just trying to give me numbers from -5 to 5.
Okay.
It will give me meaning, and those numbers they are like it will give me 100 numbers that are between -5 and 5.
Okay.
And then those numbers that it gives me, let me just try and print x. You see something here. When I print x, so
I
this
can't
is the
see
value.
okay. I can't see your screen.
You can't see my screen.
Yeah, it's showing me 3 screens. Let me see. Okay.
Are you still present? If you are present, I don't come.
It's showing me 3 screens. Me and presentation. Okay, yes. Okay, I can see it now.
So, well, if I should, I printed this one, the line space. I just printed it here. And see the values it gave me was this. See, all the values are just between -5 and 5. And
Yes.
if you should count everything, they are all up to 100. And all these values, just take the first one, the -0.5. When it comes here, you take the first one, -0.5, and just replace it by x and put it into y. You take the next one, replace it by x and put it into y. This will allow me to draw the line. This will help to draw the line. It will give me a lot of points.
What does it have to be negative R? Can it be another like a positive R or it be positive and another alphabet?
If it's positive, so it's also going to work.
You're changing 0. I meant like okay. I mean the negative R there. What does it stand for? Is it just a range?
The negative R.
Does that represent a range? Yes. Does it represent a range?
Oh, that's the color for the line.
Yes.
That's the color for the line.
Okay.
The line itself.
Because I was surprised to see negative R instead of just R.
No, that's the color for the line. If I should do it green,
Okay.
the line is changed to green.
Oh, okay. Yeah, okay.
Yeah. So that's the color for the line.
Okay, that will go.
Yeah.
So your -5 and 5 basically is a range between -5 to 5.
Yeah, -5 to 5. That's why it's helped me just.
Then the 100 is the 100 values that covers it.
Yeah.
Okay.
So this will just bring us to the end of today's session. It's very important for you. It's very important for you to understand the learning rate. So on Sunday we continue with the tutorial.
Right. Thank you.
Thank you too.